in, but I do have some qualifications. I worked with a bunch of UW Madison connected people, many of whom either got their PhD or were current faculty or are current faculty. You can see the list there, and in fact you'll be hearing from Peter and Karam later on, along with John and Ariel. But for now, why are we here? So, why do structural econometrics? This is an introductory lecture, so it seems like that's a reasonable kind of question to ask. Well, first of all, for the reasons of internal consistency. Rational individuals facing constraints in a model, fine if you want to break the rationality assumption, but how do you want to break it? Tell us how in the model and try and justify it. Uncertainty treated as a probability distribution, typically something that people in the model know or know something about, and you specify what they know. A notion of optimization within equilibrium, whether it's competitive equilibrium, monopoly, non-cooperative, maybe optimal contracting. And then there's this model that you've got an equilibrium, and then you go, here's my data. Let's pretend that my data was generated by the model. Sounds terrible, but Milton Friedman said, let's pretend that the leaves are rational and know when to turn color and drop off. So let's do that. Data generating process comes out of the equilibrium model, and in particular as a sample from the model population. Not necessarily a random sample, could be a selected sample, but from the population. And then the estimation of the parameters for the model, because you can imagine that you're saying, well, I know a lot about the model. I need to make lots and lots of assumptions. And so that's the class of things that I'm going to consider. How am I going to narrow it down? Well, I'm going to use the sample to narrow it down. And so how does the sample relate to the population? Well, things like law of large numbers, central limit theorems help us to work out what the parameters must be if the sample was generated by this model in this population. So that's what I mean by internal consistency. You don't need to go to a great person. You can just work it out logically whether it's right or not. Okay? That's why it has appeal to graduate students as opposed to people with a lot of vintage capital. Okay? So the next thing is that there's a certain elegance and transparency about this, in the sense that it may look complicated, but at least you can piece together the different steps and work out how it goes. Whereas if you don't do that, it's like, where does this come from? Okay. So the steps can be independently verified. There is numerical work. And so, yes, less discretion. And then I say, sort of in a trite way, what is numerical zero? And that sounds like, oh, come on, 36 digits, isn't that enough? Well, okay, what do we mean by an extremum estimator again? It's going to the top, right? That means a zero. And, oh, wait, did we get to a local? So there's more to it than you might necessarily think. The model itself gives a definition of causality. The model does. Causality, when you're doing structural econometrics, causality is something that the model gives you, okay? It's an explicit framework, it's an economic framework based on explicit assumptions, okay? So that is a contrast to what's sometimes called causal econometrics, in which it's a fairly open-ended question as to what are valid instruments. Is it causal or, oh, wait a minute, isn't there something out there? Where it's sort of open exploratory. Once you have a model, you're closing everything off. You're saying, this is how the world works for the purposes of my sample. So that's the sense in which causality is very narrowly defined, but also very well defined. And then finally, of course, you've got a structural model. You're telling me how the world works, at least if you buy my assumptions for the minute. So that allows you to do counterfactual predictions. What if we change the parameter this way? What if we change the policies that way? It's derived directly from the model. Clearly, strictly only applies to the model. Okay, structural econometrics in one slide back there. This conference has a theme of heterogeneity. It's one of the themes. Why? You know, we put together a theme and someone or some group said heterogeneity and policy evaluation, and everyone said, oh, that's good. It's like, okay. Heterogeneity, firstly, inspires, enriches, and actually complicates theory. You know, differences. But let's face it, think about economics. You could start out with constraints, but then the next thing is specialization and trade, right? So heterogeneity is pretty basic to, more generally, social interactions, which actually would look a little sterile if we were all the same. Maybe that's me speaking. So heterogeneity in dynamic environments opens up even more, right? Because you've got people who might invest or not invest. There's a consumption savings decision, of course. You want to spend a lot now and be poor later? Maybe. You've got your memories to live with. There's investment in human capital as well. That differentiates people. And unfortunately, living things die. So atrophy as well. And heterogeneity also arises because of differences in information that we have about the world that unfold over time. So there's sequential revelation of information. So if we're dealing with a heterogeneous population, first of all, the theoretical model is harder, right? But then it's also more interesting, and that's where a lot of the economic questions might come from in the first place. Inference is difficult, or more difficult. First of all, it complicates the interpretation of aggregated data, because you've got a bunch of different people being summed up, and you say, well, here's GDP per person or something. Well, per which person? Per which composition of people? The ones that report? I don't know. It sort of aids identification if observed. The idea is, think of a hoteling model. You've got a demand curve, and you've got supply curve, you've got something shifting supply. Well, differences are going to tell us something about the slope. So if there is what we'll call stable preferences, identification can actually aid, heterogeneity can aid identification, because you're getting different environments. People perhaps people with the same preferences faced with different lotteries. And so you can work out how they react to these different lotteries. But on the other hand, the estimation is complicated if the heterogeneity is unobserved. So there seems to be a sort of a double-edged sword thing. So Stefan's going to say more about that. How can we conduct? Policy evaluation was the other theme. Okay? I said heterogeneity is one theme. Policy evaluation is the other theme for this conference. Well, how do we even conduct policy evaluation without a model? This is a bunch of rhetorical questions, as you can see. Should the parameters of the population be determined by the thing that you're considering? There are some obvious yeses here. Next question, a little more serious. can a model be useful without being realistic? And the reason I say that to you is I've actually estimated a few structural models in my time. Almost every time you will get at different seminars, is that realistic? Oh, please. No, it's not. Of course it's not. That's why I've got assumptions in there. Excuse me. I'm not allowed to talk like that in a seminar. But what about lab rats? I mean, does anyone, we do question whether you should do this environmental stuff with lab rats, especially here in Wisconsin. Probably the environmental guys, be kind to animals week, no more animal laboratories. Okay, so that's the reason we shouldn't do experiments with lab rats. Does anyone say you shouldn't do it with lab rats because they're not humans? Of course they don't. You want to do it with humans instead? I shouldn't even say. So what is, more basically, what is realism? Okay? You know, we've got senses, we've got memory. Who decides what's realistic? That's the sense in which structural econometrics is going back to. Can we please have a look at the logic of this and see where the assumptions are and go from there? And then, is also an issue is, okay, suppose we decided what realism is, received orthodoxy, some kind of consensus that a bunch of old white men have formed. What is research? Well, part of it is challenging orthodoxy. So having a model that's not realistic is not necessarily a bad thing. The real issue is it helpful or not in being able to give light on some policy question that you're interested in? Is there a demand for what you're doing because you would like to earn some money? Okay? Or why should taxpayers be paying for you if it's not? So where do we start? Where do we start thinking about these structural econometric models? Basically, you've got a bunch of data with background characteristics, choices they make, outcomes from those choices. What kind of challenges do we have in thinking about using the data to create something useful that people will pay us for? Well, one complication, you start out with an economic model. We're typically non-linear. And so all that stuff done on normal distributions was great with linear models. But a whole bunch of reasons why you don't end up with a linear model when, of course, the normality assumption is a parametric assumption to start with. And so that's going to make things a little bit messy. Not only that, mentioned this up above, this unobserved heterogeneity thing, the data variables that we have are typically an incomplete description of what is relevant to our model. In other words, we'd like to include stuff that we don't have data on. So those are a couple of things that really kind of constrain us. So I'm going to start out and actually for the rest of this lecture, essentially follow through with a standard dynamic discrete choice model, which is a backbone for a lot of the research that's been done in structural econometrics. We'll just walk through that and see a little bit about the challenges that we're going to face as we start thinking about how do we do inference estimation, hypothesis testing, counterfactual stuff, blah, blah, blah. Okay? So we'll keep it in discrete time. Peter's going to push it to continuous. And there are capital J actions. No big deal about assuming them being mutually exclusive. Pick an action, little j, you just set d equal to 1 as opposed to 0. Ooh, I got a problem here. What do I... Good. Good. We're back in business, I think. Yeah. Okay. There's a bunch of things that determine what people might do. Z or Z, depending on where you're from. I don't want you to think about what's observed versus what's unobserved right now, okay? We're talking about a model, what the people do. So don't think of epsilons, please. It's Z they care about, okay? And so you got to transition. Depending on what Z they have, they're going to make one action versus another, and then as they do that action, that's going to affect the probability distribution of what Z is going to occur next period. So it might be something like number of births you've had. Might be whether you worked last period or not. Female labour supply is very common kind of thing for labour economists to work on, not because they're necessarily socially DEI motivated, but because there's variation in the data. Okay, if there's no variation in the data, there's nothing to look at. And so there's way more variation for females than males, so obviously, you know, we're curious. So, you know, if you had up to 5 kids, a couple of levels of experience, you know, you'd get up to, if you counted everything, about 750, if I did the arithmetic right. Add in a few levels of education, as people do. And now, and say 3 racial categories, you're up to 9,000 different values for all of these different things, okay? Just putting together all the different possibilities here, multiplying them, okay, fine. So, whoa. We will. This is a fast lecture. Sorry, I'm stuck again. I didn't mean to talk that quickly. We will. Actually, I think I need some help because we're going backwards and not... Yeah, thanks. Like the Z right there. That's good. That's good. Oh, I see. No. No. Try again. Now it's moving. All right. No, it likes me for now. I was here for a semester, maybe I screwed things up. That was a few years ago, but who knows. Z carries on. All right. Could be 9,000 different values of Z. And a very simple example, okay, of just how many kids you've got, whether you worked last period or not. Those are the things that might determine what you're going to do, because obviously your wage might depend on recent experience, stuff like that. Okay, so at some level, if we looked at Z cross, you got 81 million cells. It's sort of doable. But in many applications, basically, there are only a few cells you can get to from where you are right now. You can only add 1 year to your work experience, for example. Maybe you have twins, but usually you just have one kid at a time. You don't lose them. Once you've got them, you have to keep them. So if you work that out, actually, and you only allowed people to have one kid at once, you only got 54,000 different elements. And not only that, all of these non-zero elements are 1, or at least the additions are 1. Okay, so that, and so bottom line is that state space, how you configure that state space. Remember, what do people care about? That is the information that they have, tons of stuff. But that state space is something that you model pretty carefully. And it's something to think about a lot. You know, I said it's an art, but maybe it's machine learning, combination. So you've got these guys with expected utility, discount factor here, utility here. Only one of these D's is 1, so you're picking out which utility you get each period, taking an expectation over the future, because you don't know what's going to happen in the future. You've got a transition matrix, remember, but you don't know exactly what's going to happen. That beta really is redundant if you're setting U, if U is time dependent, but we usually put it in there just to make sure that everything's nice and bounded, and that's that way you want things to be in expectation bounded so that you can talk about a maximum. Okay. So one of the things that we typically define straight off is the value function. That's when people have solved it. Okay. How would they solve it? Using backwards induction in a finite horizon case. Last period, work it out. Second last period, given the last period, etc. And then extending that, infinite horizon, go to contraction mapping, so that finite horizon 1 is almost like an infinite horizon 1. And so we could talk about the expected value function in this case, just by asking, well, what is Z going to be, given that you take the optimal action today? Work through it. Bellman's equation is just going to give you, well, here is my utility that I get from the optimal action over here, and then I'm going to get this future stuff over there, which is just next period's value function. I've already described how we could solve this thing, so I'm not going to take any more time on that slide. Let's go to the case in which everything that's relevant to the people is observed by you. No unobserved heterogeneity at all, no epsilons, okay? Everything is observed. Perfect data set given the model, all right? So clearly, if you're optimal, you're always going to take the biggest one of these, because basically what you're looking at is the utility, current utility that I get today, plus being optimal from then on out, okay? And that's going to define, what the optimal decision rule is. Fair enough? You see all the information, you look at, here's my utility today, here's my continuation value utility for the rest of my life, starting tomorrow onwards. Take the best J. That's how I would do it. So that gives us a lot of restrictions, doesn't it? Because we look at all the people that are going from one cell to the next, given that they take J. We've got all these different Z's, we've got all these different choices, we've got all these different inequalities. Hey, we could do inference straight off, okay? And go somewhere with that. And in fact, I calculated, if my arithmetic's correct, a bunch of inequalities here, all right? And remember, I said there are millions of these, potentially, okay? Got a rich data set. So could we do that? Oh, no. We still got a problem here. Let's see. Okay, that one, you want me to switch? Yeah, go ahead.
Let's kill this one. Battles is better.
Great. Okay. So I said, got all these inequalities. Great. Maybe. Because suppose two people with exactly the same z's choose different actions. Well, what must we conclude? That they have the same utility. Right? Otherwise, one person wouldn't have gone one way and the other person wouldn't have gone the other way. We see everything that's relevant. One person went one way, the other person went the other way. It must be the case that they had the same utility. In other words, they're indifferent between the two choices. Must be. Fair enough? Now think about this data set that we have. We've got all the heterogeneity. We're seeing people make different choices, but they're making different choices sometimes when they have exactly the same z's. Actually, for a large data set, you'd probably observe everybody making every condition, every possible choice at every possible z. Might have that anyway. And if you did have that, what would you be able to conclude? What would you be able to say? Almost nothing, because they'd be indifferent. Your model would say they're indifferent. You have no empirical content. How would you be able to predict what people are going to do when they could do any one of these things? You saw all the z's. For all the z's, they do different things. What's the empirical content? What can you say? Well, they could do one of these different things. How much will people pay you to tell you that? 0. Okay? So that's one problem we would face by thinking that we observed everything that was possible. There's another problem that we would face too, because 99% of the time they're making one choice, and then there's this 1% that makes another choice. It's like, wouldn't you want to be able to say that most of the people make the 99% choice? If we observed everything and we just observed one person making the other choice, well then, hey, they're indifferent. Okay? So that's the sense in which by relaxing, or no, I won't say relaxing, by taking the view that we observe all the heterogeneity, we've got a problem because we're not utilising that information. We're just saying they're indifferent because some people choose one and some people use the other. We're ignoring the fact that 99% of the people do one thing and only 1% do the other. So the reason why we introduce unobserved heterogeneity is not to be more general. The reason why we introduce unobserved heterogeneity is because we have to. Otherwise, we'd have no empirical content. That's the reason why unobserved heterogeneity is in there. Now let's turn it around the other way. Suppose our data tells us nothing. In other words, let's suppose everything is unobserved heterogeneity. Everything is unobserved heterogeneity. What could we say? Well, again, nothing. All right? Because the data is not useful. It doesn't say anything that's relevant. And so part of this business of modeling structure is, yes, there's heterogeneity. What is important? What can we observe? What can't we observe? Those are pretty big questions in terms of thinking about how we do the modeling. Okay? No easy answers. Well, okay, I give up. We're not going to do everything with observed heterogeneity. We're going to introduce some unobserved heterogeneity. That means, straight off, that we're not going to be able to predict what any individual does. Because there's stuff that's unobserved that we don't see. Okay? And so we're margining over that. There's a probability that they might do this or a probability that they might do that, conditional on the stuff that we see and, of course, the parameter estimates that we estimate, given that they're optimizing in equilibrium. Well, straight away, the distinction between macro and microeconomics is pretty much obliterated, because we are talking about predictions for a population. That's what macroeconomists do. They usually, well, I won't say what they usually do, but they're talking about the population, right? But so are applied microeconomists. We're really talking about here's our sample, and this is what we can infer from the population. So let's now start partitioning according to what we observe and what we don't observe. Here's what we're going to observe, the x's, and here are the epsilons, the stuff that we don't observe. Haven't said anything about them yet. Haven't said that epsilons, for example, pull something right out of the air, a type 1 extreme value. Haven't said that, okay? But what we will say is that let's imagine that these are independent, identically distributed. And that's right there is a real question too, because maybe they're not. Maybe they're all influenced by the same information shock. You know, there's an announcement by the feds and, you know, interest rate's going to go down, so, ooh, let's borrow. You know? Stock prices adjust automatically. That means people are already adjusting their consumption savings behaviour because they own 401ks and whatever. Okay? Leave that aside for now. Although it's, again, important question. I'll get back to it maybe over time. And you got these x's that reflect, this is the states that we observe from, say, 1 to the end of their lives, make it simple, cap T. And here are the decisions that they make based on z, which is x and epsilon. So we could talk about the marginal or mixed probability density of going from 1z, observed and unobserved, to the next z, observed and unobserved. Okay? So we're here. And what are we going to get? Well, it depends on our action. That's going to be taken in equilibrium, optimized. So there's our optimal action. And then we're going to have a transition here. Okay? It's going to reflect the fact that here, this is what our z was today. This is our action. This is what our z is tomorrow, observed and unobserved. Okay? And so now we can ask, well, what's the probability of observing a sequence that looks like that, given the front end? I see x1, what it is today. Then there's going to be choices, x2, x3, right through the end of their life or whenever it stops. Okay? And so we're thinking about what is the probability of observing that sequence given this x1, say. I could even put a distribution on this guy too if I wanted to, but let's not worry about that. Okay? You know, where did this guy's genes come from? You know, that's the sort of x1 thing that you might want to ask. Maybe. Well, okay, you do this integration. Okay? You're integrating over all these epsilons. You've got what is going to happen at the end, and then what is going on through the middle of his life, that's given by this, okay? Integrating over all these epsilons to get this probability. And the reason why you're going to have to do that multiple integration is because today's epsilon might be how well you did in your qualifier. And that is going to affect the rest of your life. Actually, not true. But it sort of affects your choices, and then maybe actually learn something from the qualifier as well. And so you'll have this knowledge that's going on that you've got. It's not in the data set. And so we've then got to integrate over that piece of knowledge that you got from maybe JF. Sorry. All the way through to, you know, where you publish your first econometric or an IO. Okay? So that is a sense in which there is multiple integration here in general. Fine. So hasn't stopped us trying. You know, in the early 80s, we said, yeah, we got computers, we got panel data, we can do this. Big machines, back then. Big data, more than 10 observations. We are going to do it, okay? Solve the world. Come up with our structural model, and then everything will be satisfied. You know, it's like, oh, nirvana, just around the corner. Right. So you put together this maximum likelihood estimator, doing what I've just described. And yes, I'm a culprit. So was Ken Walton. You know, in this case, we're talking about updating beliefs about non-pecuniary benefits that are not observed in the data, and so you're integrating over a job match. And that leads to turnover if the match is not good. No staying with it if the match is good. You can see how the dynamics are going to play into a role here, because you're only going to learn about how good the match is over time. Well, we ran into some problems pretty quick. Ariel said, oh, look at all those integration signs. Why don't we do simulation instead? Okay? And so if you look at his patent paper, you can see that he introduced simulations to do the multiple integration. Okay? And there has been a fair bit of work since then on dealing with integration. Ariel himself contributed, but a bunch of other stuff. And in fact, John will be talking about dealing with this in terms of using finite mixtures later on. Invicta, also going to talk about this later on as well. So there's been a fair bit of work on how to deal with the integration problem that, in a very sort of brief way, I've described. But another way of dealing with it is to say, let's get rid of it. And this is John's point in the Mr. Zerker paper. Let's set it up so that there is no multiple integration by introducing this conditional independence assumption. And so here's our joint transition, okay? Here we are today, here we are tomorrow. Let's make an assumption here. Let's kill off the effect of this epsilon for future, the effect of the current epsilon has on future epsilons and future x's. So yeah, the x's which we observe, they can affect the transition next period. Okay? But the epsilons here aren't affected by anything that went on in the past. They're only affected by the current x. So we're splitting things like that. All right? And so this assumption is widely used in the estimation of dynamic discrete choice models. If you don't use something like that, you're going to be back into the integration question, not saying, not making a decision, not making it, giving you advice about which way to go. But those are the kind of considerations you face. So let's start with, let's continue along this line for a minute, because a lot of work is actually based on what happens when we appeal to the conditional independence assumption. So where we go? We got the U here and the epsilon here, and you might think, you know, where is the assumption? Because we could just take a conditional expected value of U and, what is the conditional expectation of utility given the x's that you face and the j's? Let's take that. And we'll call that the U. And then this epsilon will just be the residual of the actual U minus the conditional expectation of U. We could do that, right? Nothing wrong with doing that. The kicker really is that we almost always put a functional form on the epsilon, and there's a reason for that. It has to do with identification. We'll talk about it later. So we've got to make sure that the problem's well defined. Nothing gets too big. In fact, if the x's are finite, they don't go out to infinity, you're kind of fine. And so here we have a more standard problem with the x's and the epsilons as opposed to the z's. We've introduced unobserved heterogeneity, but not only have we introduced unobserved heterogeneity, we've appealed to the conditional independence assumption so that those epsilons are not going to have too much effect in the future. Okay? Only affect the choices right now. So in this kind of context, we again define the social surplus function. And here the social surplus function has a slightly, well, you can see what we're using here. At the beginning of time t, we see the x's. We haven't yet seen the epsilons. Those epsilons, jointly with the x's, are going to affect what choices we make. And we're going to make the optimal choice, and that's why, you know, we've got a D0 here, DO here. But we haven't seen that epsilon yet, let alone the future epsilons. And that's why we're integrating over those possible choices. Okay? Because we haven't seen our epsilon yet. We do know our x, and we call that the social surplus function. And then we can also have something like conditional value function, which is everything but the epsilon. Okay? Everything but the epsilon. So now think about a random utility model, static model, McFadden. Maybe it's no accident that John has a PhD from MIT. Okay, see the connection? Think about a static model with a utility there, a U plus an epsilon. Think logit, guys. Okay? The only difference here is that you've got a V instead of a U. And the easy way to see that is, okay, set beta equal to 0. All right? Now you have, what does the guy do? Well, he picks his biggest U plus epsilon j. Okay? That would be what would happen in a random utility model, static model. Okay? In this world, you've got to worry about the future too, because you do have a future, I hope. And I know. Hey, it's longer than mine. So then you've got tomorrow's social surplus function in there, which of course will be integrated over the x that you're going to draw when you take your action j. Right. Now we can integrate over these, what you might do. We don't know what you're going to do yet. And that will give you a conditional choice probability. All right? We're going to come back to that. We can extend this. We can push this out. This is, again, something that Victor's going to elaborate on further tomorrow, I think. You've got a dynamic game. You've got I players making a bunch of different choices. State variables for the game, okay? And then they're moving from one period to the next, which depend on not just what I do now, but what everyone else does as well. Okay? So here we have set of state variables for the whole industry, all the firms, okay, with their capitals, endowments, whatever. And they're thinking about, well, each firm is thinking about, well, what would I do now? They see all the X's, the industry configuration, okay? They're going to make their own choice, okay? Given what the other guys do. Nash equilibrium, actually a refinement of Nash, Markov perfect. But basic point is, it's a best response to the rest of the world, okay? Which, in this case, the rest of the world means the other firms acting in equilibrium. So this is our transition probability. And so you're going to get a utility that depends on what everybody does, including what you do. There's the disturbance that you get, still appealing to the conditional independence assumption over here. You're making your decision at the same time as everybody else is making their decision. There's incomplete information. You see your own epsilon, you don't see other people's epsilons. But you do know the distribution that these other epsilons are coming from. You do know how to solve their decision problem as well as your own. I teach MBAs, strategy, and one of the first points I make is telling people many times to try and work out what the other people are doing. What are their payoffs? What's their information set? How are they going to react? Don't make your own decisions without working out what these guys are trying to do. I can't help it. I believe this stuff, and so that's what I teach. And they still pay me for it. So, here's our analogy to the single agent setup. You got a conditional choice probability. Okay. Because you're thinking about, here is the industry. Here's what I might do when I'm optimally solving things in this equilibrium. And over here, this is part of the rest of the world. All of these guys are solving their problems, same way I solve mine. And that is also helping to determine what's going to happen next period. Here are the probabilities that they might move, they might use. So in this setup, you've got an individual optimization problem, and now what we're going to do is imagine that we don't know what these other guys are going to do yet. This is the utility that I would get if they did the other things. I'm just going to define the expected utility that I'll get here. Okay, that's the expected utility I'll get when these other people do their thing and I get the use. And then we got a transition function here that says, well, what's going to happen to the industry stuff? Well, it affects what I do, and actually there shouldn't be a little I there, that's a typo. Here's the industry today, and then everybody else is going to do their stuff. They're going to influence what's going to happen for the industry tomorrow. You know, I am number one, so to speak. You can tell the MBA students that, but there are these other fringe players out there. They're called rivals and competitors. They are going to also affect what's going to happen to the industry tomorrow. So that is going to affect the transition that'll tell me where things are going to be tomorrow for me in this Nash equilibrium. Okay? And so when you look at it like that, you can see that this problem that each of these agents is facing in its Markov perfect equilibrium is the same as the individual problem that we talked about before. There's still some questions of how you untangle this from this. Still some questions about how you do the counterfactuals. But in terms of the estimation, we could proceed that way. Well, how should we go ahead? How should we go ahead with this stuff? I've described the problem. I've described a prototype problem, if you like. And I said, these are the kinds of challenges that you face, okay? Where do we go in terms of estimating the parameters for this structural problem, structural econometric problem, that I've just described? And there are various approaches. So let me at least indicate some of the things that have been done. Okay? First of all, we could integrate the model solution into the estimation routine. Okay? And Bertel is going to describe an approach of doing that, and Fedor is going to be talking about that later too in the week. You get the maximum likelihood estimator out of that. And for sure, given the model's identified, point identified, that will give you asymptotic efficiency. Let's be clear, that's of course, maximum likelihood doesn't prove identification, but given that it is identified, it'll give you asymptotic efficiency. And not only that, the fixed point algorithm that you've got to in the estimation doubles as moving forward with the counterfactuals. Okay? We could separate the inference from the model solution. Okay? So that's what I'll be talking about, and also Peter later on today. Here we're exploiting the model data generating process without actually solving for it. That gives identification conditions in general, not identification in the sense that what can you get out of this model with this data? Less efficient, but faster estimates. And it requires the model solution to compute counterfactuals. Natural question to ask is, well, what if you're going to compute the model anyway? Well, why don't we just do an estimation? The question, of course, is how many times? You could combine these two approaches, and that's what Victor will be talking about later tomorrow. I'm not trying to schedule it too early. Tomorrow, there's been no change in schedule. In taking pieces of that, and then perhaps only doing one iteration to get maximum likelihood estimators after taking this approach to start out with. Or you could go even further. You could say, why don't we actually disconnect the sample variation from the population probabilities? And it's like, in my class at Carnegie Mellon, I would shudder. But here, you need to be a little bit more diplomatic. And so the argument is that we might get numerical values from published empirical work, or perhaps generate moments from the data, from perhaps aggregate data. And in that way, get some numerical values which we think are relevant to the model that we're looking at. All right? And so we're not typically going to get estimates of precision that way. And the argument for doing this is that you would argue, perhaps, that the sources of imprecision and misspecification that I'm most concerned about do not come from the fact that the sample is relatively small and hence I'm getting standard errors and whatever from things like central limit theorems. It might be that the lack of precision is coming from things that I don't have data on. And so even at reporting asymptotic standard errors and hypothesis test is like, not so relevant. Okay? And that's why I can't afford, Bob Miller, can't afford to beat up on my macro colleagues at Carnegie Mellon too much. Because they are making points about what technology is going to do in the future, how demographic change is going to affect what people decide. And we don't have a ton of data on that, and yet that's something that we care about a lot. Sort of bang, Bob, just pull in a little bit, go back to your corner, because you are talking about a stationary model or a model in which you don't really have a whole lot of technical change in there, and even if you do have technical change, you're making half of it up because you don't have data that explains how that technological change process is going forward. Okay. So that is where there's an argument. Okay? We are going to have our differences. It's okay, guys, providing you just stick to the foundations, belong to the church, you're good. Okay? We don't toss out people that much. So what are relevant factors for this debate? What kind of data do we have? How much? Okay? This is going to affect the choice of estimation methods. What about the complexity of the model itself? How many times can we afford to compute it? Okay? Literally, how feasible? What is the sensitivity of the estimates of the underlying assumptions? That's what I was talking about a minute ago with the calibration stuff. And is the sample variation related? An important factor in assessing the precision. What's the specific policy question? One of the things that economists are supposed to be able to do is basically predict something about social interactions and how policy will affect staff and all the rest of it, okay? And we can see what a great job we do as economists by, for example, looking at yesterday's news clip from the Wall Street Journal and various other places that said something like, gee, the number of jobs created this last month or quarter was actually a lot less than what we expected. We can't even predict what 1 month ahead employment's going up or down. We cannot predict very well what the inflation rate is going to be 1 month ahead. 1 month ahead. So let's be clear that some things we probably have quite a lot of precision on, other things very little. And that's not surprising. Go to the medical profession, cure for cancer. Yeah, right, coming. Maybe. Perhaps. Scientists have trouble discovering new stuff. So why is it so surprising that economists working with limited data also have trouble. It's not surprising. And so part of structural econometrics and where it's going, all of its limitations, comes from my graduate student days, prehistoric times, when Bob Lucas, outer suburb of Madison, campus, Hyde Park, was lecturing to us. Here I was, attending graduate student, of course. And in the room was Tom Sargent. Big Tom Sargent, listening to Bob Lucas as a student, just like us. Already a full professor at Minnesota, on airline covers and what have you, not quite Nobel Prize, but soon sort of thing. And Lucas was explaining what Sargent had done. Again, it's like he can do that, meaning he's not going to let Tom do it, Professor Sargent do it. And Lucas said, well, this has some Keynesian elements in it. I remember that. It's like, yeah, bad news straight off. This has some Keynesian elements in it, but he's going to fix that soon, and then we'll be able to predict what's going on in macro. No problems. Look at me now. I was a graduate student back then, looking like you, not like this. Still hasn't happened. Still hasn't happened. Assistant Professor Herb Simon. I'm listening, first year at Carnegie Mellon. Herbert Simon already has Nobel Prize, of course, telling a bunch of master's students and me, a bunch of other faculty sitting there dutifully, what's going to happen in the future. You guys, he told the MBAs, you guys aren't going to have any jobs in about 10 years' time. Yes, that's really going to help our fees, student fees, right? Saying artificial intelligence is going to be taking over. It's a little bit too early, right? But the point was, both of these guys was claiming they had, excuse me, big answers to big questions, okay? It's not obvious what kind of questions economists, when they're not being politicians and not being paid consultants, but just acting as research scientists, what kind of things we can actually talk to, okay? And I think it is useful to separate those roles out. I have no problem with people lying their heads off. That is a standard thing that humans do all the time to sort of, mess up information. You expect that, okay? In any kind of IO kind of application. But it's important for you guys to think about what you're doing, what you think you can say something about versus what you think you can't say something about. Because that is defining the agenda about where we think we can move. So that's what this is about. And I'm going to end early because I know we are going to start early, right?